Okay, let's talk about Lewis structures. So when we talk about Lewis structures, we need to talk about the octet rule. The octet rule basically says that atoms are most stable with 8 valence electrons. Um, we will break that rule, and we'll talk about when it's appropriate to break that rule. You may sometimes hear people mention the duet rule, which is just in reference to hydrogen. Hydrogen doesn't need its own rule. Just understand that hydrogen can only support 2 electrons when it's involved in a bond. You may hear people ask, why doesn't helium form bonds? And you may hear the common defense of its valence electrons are full, its orbitals are full, so it can't form more. That's kind of a naive and simple explanation. When you think about it more in terms of attraction, in order for helium to add another electron and form a bond, it would have to um, place that electron in a position where it's not as attractive as it is to its own valence electron. So the likelihood of electrons being added onto helium is small because of the additional repulsion it would create, and ultimately it would result in an unstable structure. The rules for Lewis structures. These are rules we've learned before, so I'll go through them quickly. First, we'll count the number of valence electrons in all the atoms. We'll use 2 electrons to form single bonds and bond singly each atom, and then we will fill remaining electrons on the periphery first to fill their valence shells. Peripheral atoms don't break the octet rule. Um, and of course, hydrogen is happy with 2. Excess electrons are placed on the central atom in pairs. Any shortage of electrons tells you that multiple bonds, like a double or triple bond, may be needed. So let's do hydrogen sulfide. First, we're going to count valence electrons. There are 8. And then we will draw single bonds from the central atom to each hydrogen. How do you determine central atom? Generally, it's the thing there is one of. Generally, if carbon's involved, carbon is central atom, and that's about it. So when we look at this setup so far, we have singly bound sulfur, so we have 4 electrons that have been used, and we have 4 more electrons. Hydrogen can't take more electrons. Each hydrogen is 2 electrons so far, so then we will place the last 4 electrons on the central atom, which gives sulfur its 8 electrons, and that's that. Carbon dioxide. Carbon dioxide has 16 valence electrons. There's the skeleton drawing of carbon and the 2 oxygens surrounding. If we go ahead and place electrons until we run out around the periphery, we see that we don't have any issue there, but we run into the fact that carbon only has 4 electrons in that drawing. So that's not going to work. We ran out of electrons. We're going to have to form some multiple bonds. And what we do is, instead of doing single bonds, we do double bonds, and that's going to leave us with a structure that obeys the octet rule and looks stable. So there is our big check mark there. We'll talk about formal charge in the future here, but essentially what we need to see here is that each atom has met its octet. Let's do ammonia the same way. Here's the skeleton drawing. Notice we've already used 6 electrons. We only got 8. Hydrogen can't take more. The last 2 must go on the central atom, nitrogen. There's ammonia. Hydrocyanic acid we're going to draw together. Here is our skeleton drawing. Oops. Just a peek. Our skeleton drawing, let's just do singly. Let's get this right. There we go. So at that point we have 10 electrons. We can't put more around hydrogen. We've already used 4. 6, 8, 10. The problem there again, carbon only has 4 electrons. We're going to have to move these 2 in. We'll have 6 on carbon and now 8. So let's redraw. And then there's a pair of electrons here. And carbon now has 2, 4, 6, 8, as does nitrogen. That's a stable drawing. Nitrogen, hyponitrite ion, 10 electrons. There we have so far 2, 4, 6, 8, 10. Again, not enough electrons. So we need 4 more to go on nitrogen, so we will form multiple bonds. In this case, a triple bond. And that we need to write our ion in brackets. So 2, 4, 6, 8 on nitrogen, 2, 4, 6, 8 on oxygen, a +1 charge. Just so you can see, note that nitrogen has 1, 2, 3, 4, 5 electrons. That's appropriate for it. This is the formal charge discussion. You can reflect on this later. And that oxygen only has 1, 2, 3, 4, 5. I'm counting oxygen's contribution to the molecule, and it shows that oxygen only contributed 5. And so our formal charge is located on oxygen here. Nitrogen is just fine, and that is A-OK. Carbonate. Carbonate has 24 valence electrons. So to draw this, we're going to draw single bonds on all of our carbon to oxygen. And so once I've drawn the single bonds on oxygen, then I will use the rest of my valence electrons filling up the valence shell for the oxygens, and that gives us 24 electrons used. And again, we're short on carbon, so we'll borrow electrons from one of the single bond, or from one of the oxygen atoms, and replace. This will allow us to double bond one of the carbon oxygens, and that's going to leave us with, notice we have a 2 minus charge here. That's going to leave us with formal charges on each oxygen. Okay, we'll get into formal charges again later, but what that means is 2, 4, 6, 7 electrons contributed by oxygen. Again, oxygen only has 6 valence electrons, so each one of these oxygens in the carbonate molecule has its formal charge there and there. That's the reason carbonate has a -2 charge, is those formal charges on each oxygen. Now, we'll talk about the formal charge and how we calculate that shortly. Some exceptions to octet rule. Boron is stable with 6 valence electrons. Please correct your notes, 6 electrons. Beryllium forms compounds with 4 valence electrons. Boron trifluoride has 24 valence electrons, 3 from boron and 7 times 3 from fluorine. When you bind singly, what you will find is that you will use all 24, stabilizing the octet for all of these. And your temptation may be, hey, we've only got 6 on boron, we need to borrow and form a double bond. You could do that, but the fact is boron is actually stable in this configuration. Okay, so this is A-OK as it is. Beryllium, similarly, you might say, well, beryllium's metals, it doesn't form covalent compounds. True, but some of its bonds have lots of covalent character, and so some of them do get drawn in this manner. You won't ever be asked to decide how it bonds. Just that beryllium is stable with 4 electrons in what would appear to be a covalent structure. Elements beginning with phosphorus in the periodic table, element number 15, may exceed the octet rule and support more than 8 electrons when acting as the central atom. For example, sulfur hexafluoride. You, again, are singly binding off the central atom each of the peripheral atoms. Okay? You may be tempted to see 6 there and draw 4 and then maybe string fluorines off on one of these, and that's not the case. Sulfur is able to form multiple bonds more than the octet, and so we will use all of the 6 plus 42, 48 electrons here, and you'll see that each is just singly bound, and that's all 42 of our electrons. This is sulfur hexafluoride. Anything from phosphorus to sulfur to chlorine, arsenic, selenium, bromine, and even down into krypton and xenon, noble gases that form covalent compounds. Further exceptions, the size of the atom allows more electron domains. The larger the atom is, the more domains you're allowed to have or able to have electrically. Just think about it in terms of repulsion. A smaller atom will not have as much space around for the repulsion to be permissible. Elements in first or second period of the periodic table are not going to be able to exceed the octet rule. Iodine, or the triiodide ion, is quite interesting. It looks like this. And so we've got singly bound iodines. And what ends up happening is we have those bonds like that, that central atom, and we've used up 1, 2 of iodine's 6 electrons, or 7 electrons, 1, 2, 3, 4, 5, 6, and 7, and it's got 1 extra electron, so your formal charge is right there on the central atom. So it's got 3 pairs of electrons and 2 bonds. Chlorine trifluoride and radon dichloride are also quite interesting in terms of their ability to break the octet. We'll look at those further when we do valence shell electron pair repulsion. Resonance. Often when we draw structures with more than 2 bonds, we find that there's more than one way to draw it that obeys the octet rule. that's acceptable. And so basically what we need to say about that is the actual structure is going to be a combination of all three, where electrons are able to move in space. And so this helps us understand, in terms of the localized model, how electrons move. And so if we look at benzene, which is a ring, what we see is we have alternating double and single bonds around the ring with hydrogens at each post. Notice that in this format we have the double bonds here, 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 and this one we have here, here, and here. The reality there is that these electrons are in pi bonds across all the dimensions, and essentially all occupy the same space. And so you'll often see those electrons just drawn as a ring above and below, and this is to represent the resonance. Is this just that the electrons are in all those positions all at the same time, or all throughout time, and essentially form an electron space. This is the delocalized model, and this is more of the localized model. You'll sometimes see benzene drawn like this to represent that the double bond can be at any three of the poles. This is sulfur trioxide drawn three ways. Notice the double bond moves from this position to this position to this position. These are three different resonance structures for the same structure. Bond length is found to be about 1 1/3 on average for all three, which makes sense because sometimes the extra electrons are in all three of the positions, that over time the average bond length would be the average of all three. So sulfur trioxide has three resonance structures. Some substances have 6 or 8 or 10. Finally, formal charge I wanted to get into is used to determine the most accurate Lewis structure considering stability of each atom on the molecule. When we draw a structure, we're going to calculate formal charge for each atom. It's the difference between the number of valence electrons on the free atom, for example, nitrogen would have 5, and the number of valence electrons assigned to the atom in the molecule you've drawn. Okay, so if you draw a molecule with nitrogen bound to hydrogen, this is called ammonium. You may have heard of it. Note that nitrogen in this molecule is attributing 4 electrons. It is contributing only 4. It's supposed to have 5. So on the atom, we've got 5. In our drawing, we've used 4. So our charge is +1, which is consistent with the ion's charge. All ions have a formal charge on one or more atoms. Okay? If a molecule carries a formal charge, that makes it a very reactive molecule. And you'll find that to be consistent with things you already know. A couple things about formal charge. They're most stable, or atoms are most stable when they achieve formal charges as close to 0 as possible. Any negative formal charge are expected to reside on the most electronegative atom. So where the extra electrons lie, it should be on the most electronegative piece. The sum of the formal charges on the atom of a molecule must equal, on the atoms of a molecule must equal the overall charge on the molecule 0, or the charge of the ion. As far as formal charges go, you only need to consider them on the AP exam if they're specifically addressed. So let's draw sulfate. First and foremost, you need to recognize you've got 6 plus 6 times 4, 24, plus 2 electrons, which is 32 electrons. So we're going to draw this. And if we fill the valence shell, we've used 32 electrons. Okay? But what you should also notice immediately is that each oxygen has, 2, 4, 6, 7 valence electrons. So each oxygen in this drawing has a -1 formal charge, and our sulfur has 4 electrons, which makes it +2. That's terrible. You have a formal charge on every atom, and that is undesirable. So how can we remedy this? Well, recall that sulfur is beyond phosphorus on the periodic table, and therefore can form bonds with more than 8 electrons. And so what we can do is doubly bind 2 of these to remove the formal charge on sulfur and just leave charges on 2 of the oxygens. So let's do that. Let's get rid of the charge on these 2 guys and get rid of that. And let's rob a pair from each one of those and then form double bonds here and here. Now keep in mind, sulfur can do this. It can form bonds with more than 8 electrons. So we have a formal charge here and here. But keep in mind, we're dealing with sulfate ion. That's okay. We should see 2 atoms with -1 charges for an overall -2. That is the Lewis structure of sulfate. And finally, this is the amide ion, NH H. We've got 5 plus 2 plus 1 electrons. We've got 8 electrons. So far we used 4, 5, 6, 7, 8. Where is our charge located? It's probably on the most electronegative atom, and that's confirmed. 1, 2, 3, 4, 5, 6 electrons, minus 1 charge is there, and there we have that. So that concludes our lecture on Lewis structures and drawing structures. We'll see you on the next one.